Hey guys, today we're starting vectors. Maybe you already hate them because linear algebra is painful, but we're going to fix that. First, let's get through some basics and then on to the fun stuff. What's the difference between a scalar and a vector? Scalars are quantities that we can express with just numbers. Vectors need both a number and a direction to describe them. We write them with a little arrow over the top. Visually, there's a few things that help us define a vector. This is vector f. It has a length of 5 newtons, and it has a tail at the point O, which is its origin. This tail goes along the reference axis. The vector itself goes along the line of action. The line of action helps us to define the direction of the vector. In this case, f is oriented 30 degrees counterclockwise from the horizontal. Lastly, the vector's sense is indicated by the arrow at the head of the vector. This vector has a downward sense, as opposed to an upward sense. So we could say that vector f has a magnitude of 5 newtons and is oriented 30 degrees counterclockwise downward from the horizontal. Here's some quick facts. If vectors are collinear, meaning they have the same line of action, we can add and subtract them like numbers on a number line. When we multiply a vector by a scalar, we change its magnitude without changing its direction, just like normal number multiplication. Lastly, we need to remember some trigonometry. The sine law says that for a triangle, the ratios of a side length over the sine of its opposite angle should be equal for all 3 sides. The cosine law lets us solve for a side length if we know the other 2 side lengths and the angle that is opposite the side length that we're looking for. Now for the fun. We want to add vector A to vector B to get a resultant force. A resultant force means that if we were to push on an object with force A and force B, it would be the same as pushing on that object with the resultant force. Force A and B together are equivalent to the resultant force. We're going to solve this problem using the Parallelogram Law. To start, we draw the vectors tail to tail. After drawing our vectors tail to tail, we go from the heads of each vector, drawing lines that are parallel to the opposite vector. When these lines intersect, they form a parallelogram. Now we can draw our resultant vector. This goes from our tails to the point where our lines intersect. Now, because we have a parallelogram, we know that this side must be equal to this side. So we can redraw our vector B over here. Now we have a triangle, which is magical because it gives us power. We know our side length here and our side length here. We're looking for our resultant length here. We can use the cosine law if we can figure out what this angle opposite our resultant is. Well, from geometry, we know this angle is 50 degrees, and this angle with the horizontal must be 30. So our angle R must be 100 degrees. Now we can use the cosine law to solve for the magnitude of our vector R. We plug in our numbers and we get that to the nearest tenth of a newton, R is equal to 58.3 newtons. Now all that's left to do is find its direction. The angle that we're looking for is angle theta that R makes with the horizontal. To find theta, we're going to have to work backward with our triangle to first find the angle phi. Phi can be found using the sine law because we have R and the angle opposite R, and we have B, so we can solve for phi. Now, once we have phi, we can work backward. Phi is made up of theta, which is the angle below the horizontal, and 30 degrees, which is the angle in our triangle above the horizontal. So we can solve for theta, and we get that theta is equal to 0.4 degrees down from the horizontal. That means that we can say our resultant, R, is equal to 58.3 newtons, oriented 0.4 degrees clockwise downward from the horizontal. Now let's do an example using triangle construction. We want to know the magnitude and direction of the resultant force of A and B acting on this hook. If we were to use the parallelogram law, then our next step would look like this. We would draw the vectors tail to tail. Then draw parallel lines from the head of each vector until they intersect each other, forming a parallelogram. Our resultant is the straight line from the tails of our vectors to our intersection point. Using our parallelogram, we know that the side opposite our vector B must also be equal to B. This gives us a triangle, which lets us use trig to solve for R, like we did in our last example. Using triangle construction, we can skip some of the steps we used to get to the triangle. This time, in the first step, draw the vectors head to tail. Now our resultant vector goes from the tail of our first vector to the head of our second vector. This looks familiar, right? Using triangle construction gives us the same result as going through all the steps of the parallelogram law. Okay, now let's solve this sucker. Like last time, we're going to start with the cosine law to solve for the magnitude of R. But first, we need the angle in our triangle that's opposite to R. This would be equal to 180 minus 35 minus 40, which gives us 105 degrees. And we get that the magnitude of R to the nearest tenth of a newton is 72.8. Now we want to find the direction R relative to the horizontal. That would be our angle theta. So to get theta, we actually have to find the angle phi first again, so that we can keep working with our triangle. We already solved for R, which is 105 degrees, and we know the magnitudes of our vector R and our vector B, so we can rearrange this to solve for phi. Now we can work backward to solve for theta. And we get our final answer, which is that the vector R is equal to 72.8 newtons, oriented 19.6 degrees counterclockwise from the horizontal. Ta-da! Thanks for watching. Come back next time for a spooky Halloween video on vector addition examples.